right. So I like, we're ready. I like to keep you guys aware of where we are. This whole column C here is first quarter. That's right. We're still in first quarter, even though we're not. Does that make sense? So we just did geological stresses. We have faults, earthquakes, and seismic waves to finish up the quarter. Does that make sense, Ike? Okay, shush. When we're done with this, today, that means Monday, Tuesday is review time. So I'll probably get you a worksheet to help review on Monday. Tuesday would be free for you to study however you see fit during class, bookets, whatever, quizzing each other. Plate tectonics test is next Wednesday, Thursday, or Friday. I have not pinned it down, but you have been warned. I'm shooting for Thursday, but if for whatever reason I need to move it, I can. Okay. So with that said, faults and earthquakes, those two lessons, we're going to go through them. And if you have a question, please ask. Seismic waves is the one we're actually going to assign and do the questions mandatory. Does that make sense? I have had, believe it or not, I've had a couple students that, like, can I still do the questions for faults? And yeah, that's just good practice checking on learning, right? On your own. Okay, so faults first. Let's go back to faults. Do we already know what faults are? Have we not mentioned faults? Haven't we mentioned faults? Yeah, we have. What's a fault? It's a break in the rock that results in movement. Yeah. So a fault is a break in the rock and it moves. That break has some motion there. Here is a picture of Crystal Spring Reservoir. I think that's what it's called. Yeah. In California, near San Francisco, along the San Andreas Fault. So there's a depression, a low spot. I don't think I'd call it a depression. A low spot caused by the fault. And that had a spring running through it. And then what do we sometimes do with springs or rivers? We dam them to create reservoirs. Cool. So that's what happened here. Skimming through, guys, I'm blasting through as fast as I can so we can get to the actual assignment. This should be review, but if you're docking, you might miss it. You might miss something. Fractures. A fracture is a break, yes? In the rock. Similar to our bones, they can break. So rocks can break, bones can break. There's two major categories of break. There is like a simple fracture where there's a crack, but there's no motion. Or there's what's called a compound fracture. Everybody knows what that is, right? So that's a bone break that it has moved. And you'd have to splint that for sure. Otherwise, it's going to move around. Has anybody ever had a broken bone that went through the skin? Yeah. You did? Where was it? Ouch. So that's a compound fracture. That's pretty darn obvious, right? Absolutely. So with rocks, you can have a break, a fracture with no movement, and that's going to be called a joint. A joint is where you have no movement on either side of the fracture. Okay, but if there is movement, then we call it a fault. Okay, so a fault is just a break that has movement. Well, if you have a break with movement, what's that going to cause? A little bit of a shake, perhaps, right? An earthquake. Good. Dip, slip. I'm not going to go too much in the wording on it because they talk about dip and slip and dip. It gets crazy. Basically, when you have a break and that movement can be at an angle. It can be more vertical. It just depends. I like this image the best. They have, I don't know if these are tourists or students, standing here, and they're looking up at this hanging wall. That's the term for that, where you had a break, and one part of the land went up in relation to the other. So this is called a hanging wall. Hanging walls came in handy early mining operations. Rather than having to dig in somewhere, I mean, you've got exposed rock right there. There might be minerals that you could get to and actually extract pretty easily because you can just stand there and hammer away. Hanging wall, that term comes from they would hang their lanterns on the side of the wall there, apparently. I read that somewhere. Strike slip, we've talked a lot about strike slip, yes? San Andreas being the most famous example. I find this really interesting. So they've got this image and there's this fence line, and the fence line the fence was in along the fault, and it slid. So what are they going to do? These neighbors, there's probably a property line, who knows? And are they going to just have to put a little section of fence there to close it back up? No. Who pays for that?
Government.
Oh. Whose land? This moved over. Is this land now on this other neighbor's property?
No.
Whoever built the fence is theirs now? Who's going to probably have to get involved here? The government's not the answer for everything, folks. But we do have a court system, right? So if they argue over whose land is whose, they might have to go to like a property lawyer and figure out what the rules are. And then if there's still a dispute, they'd have to go in front of a judge, perhaps, to figure out, okay, what's going on here? This river or stream running over the fault, you'll have the river detached, but the water's still wanting to run downhill, right?
Right.
I've had it. The river's running and it gets detached. So the water's going to want to run where? Downhill somewhere. So if it's downhill this way, it's going to go, or if it's running downhill this way, it's going to turn that way. Okay? So you'll have right angles where the river has changed direction because of the fault line. Okay? Yeah, it is kind of neat. All right. San Andreas, we talked about. Summary, we're already done with the lesson, folks. Summary, if it's not in your forehead, it's in your, needs to be. A fracture with no movement on either side of the joint. If there is movement, it's called a fault. Good. Dip slip faults show vertical movement. In a normal fault, the hanging wall drops down. The one we looked at is a reverse fault. Strike slip faults have horizontal motions due to shear stress. All right, moving on. Any questions on those? Okay. Earthquakes. Here we've got a picture. Be quiet, Flexi. GeoGuessr time. What city do you think that is?
France.
France? Okay.
San Francisco.
It is San Francisco. San Francisco in 1906. What happened in San Francisco in 1906? There's an earthquake. So you can't see it well in this image. On my screen over there, I can. Right here is a piece of furniture, and I am 90% sure it's a piano. And then right above it, there's a picture still hanging on the wall. Didn't fall down. But I can just imagine, like maybe somebody was sitting there playing the piano, and then it would have a shake, and all of a sudden the wall right there falls off, and they're probably like, okay. They kept playing. Well, it's the little lid over the keys is closed. Doesn't it look like a piano? Yeah. That's what I'm saying. Anyway, what do you not notice? 1906 San Francisco. What do you not notice along the sides of the road? What's often parked along the curb? Cars. I don't see any cars there. It's 1906. The car is fairly newish. And they're relatively expensive when they first come out until who does the assembly line thing makes it more affordable. Good, Ford, yeah. You can see some of the folks, what they're wearing, very, very early century. Yeah. We got a bunch of people just sitting here in chairs. They're just, well, I mean, they don't want to go back in the building because there might be aftershocks, right? Maybe debris fall on them. So they're just sitting outside. What's this stuff back here? Smoke or dust?
Dust.
Or both?
Dust.
So after earthquakes, what often start? Fires. So I want you to think about San Francisco, 1906. 1906. So San Francisco is a city that is being built and built up big coming into the turn of the century. So they're incorporating brand new technologies into this city. It's a cutting edge city. They're not really aware though that they're on a major fault line. So they're building this city, not really building in earthquake proof stuff, but they have this cool new technology. So for example, they have water lines running under the streets, right? You can actually turn on a tap at your house. No. I'm just saying they have indoor plumbing with running water. That's nice. It's modern. They also have pipes running gas into their homes so they can cook with it and heat their homes with it. San Francisco doesn't get that cold, but yeah, they've got natural gas. In an earthquake, can those natural gas lines break? And now what do you have coming in? You've got natural gas, which is flammable. If there's a spark, you'll have a fire. So a lot of the damage caused from the earthquake was actually caused by the fires from the broken gas lines. Now, what do firefighters generally want to use to fight fires? Water. What also broke in the earthquake? The water lines. So what are the firefighters supposed to do? Dirt? It's not very quick and easy to put out a big fire with dirt.
Take it from the ocean.
They don't. So the firefighters, the emergency workers at the time, really their main concern would be getting people out of buildings, maybe some rescue going on, right? Making sure people are safe as possible. The fires are going to burn. I guess if it was a chilly morning, right? Stay warm by the fire. Okay, moving on. I just talked about all that. Causes of earthquakes. Yeah, you've got a break in the rock, causes a shake. I'll talk about elasticity in just a bit. Focus and epicenter. Do you guys ever get those twisted? No, you're good. So what's the difference between the focus and the epicenter?
Is where the earthquake happened. Like where it or maybe.
So the focus is where the break occurred, the rock break. Okay, where the fault is, that's the earthquakes. So that's the focus. Directly above the focus is the epicenter. That's where you're generally going to have the most damage to structures because we build on the surface of the earth, right? We're not like Morlocks underground, although we do have some underground structures. Anyway, yeah, I think you were right, but opposite. Yeah. Good. Elasticity. Rocks are kind of like this ruler. I can bend the ruler. You see how I'm bending it a little bit? Anybody see that? And if I release the pressure, or if I release the force, it will go back to its original shape. Do you see that? Okay. I can bend it and let it release, it'll go back. This comes into effect with tectonic plates. One way it can is imagine there's a glacier building up on the plate, adding weight, right? Frozen water adds weight. Would it perhaps bend down under the weight? Okay. As it's loading up, bending down under the weight, do you think there might be some cracks form and maybe some earthquakes from that? So that's one way you can have an earthquake inside of a plate rather than just on the boundaries. Does that make sense? And then again, so like that's during an ice age, right? The glacier's building up. We're still in the ice age, aren't we? Because we still have glaciers, but we're in an interglacial period where the glaciers are melting. So wouldn't they be going like this? The crust is rebounding right now, okay? So whenever you see something about rebound, that's what they're probably talking about. And as that crust is rebounding, what might happen? Earthquakes. You might have fractures again. Okay, cool. So that's what they're talking about there. Focus and epicenter, yep. Focus is where the break happens. Epicenter is directly above. This is him doing that. He intentionally gets to a point, he says, there's a point where the ruler will stop being elastic and it meets like a point where it becomes brittle, right? Because it can only stress so much. I started doing that and I didn't want to break it, but I went too far and I ended up breaking on accident. Anyway, I found the point, the limit. Anyway, yeah, that's my favorite ruler too. All right, summary. Sudden release of energy stored in rocks causes an earthquake. The focus is where the rocks rupture or break, fracture. The epicenter is the point on the ground directly above the focus, and most earthquakes are shallow, just a few miles deep. And those are the ones that do the most damage because they're closest to the structures. All right, moving on to the last lesson, folks. Last lesson. Shh. And I'm going to go ahead and assign this. Could you do me a favor and not start the questions until we've gone through the material? Could you? Thank you. I really would appreciate it. All right, so got it. Let's go up to the top. We've got some ocean waves crashing. Cool. Are seismic waves like ocean waves? In some ways, yes. Could you sit up, please? Ocean waves travel at the interface between the surface. Guys, we don't want to flood her with blessings from a sneeze. Okay, maybe one would be good. Okay. Interface between the sea surface and the atmosphere. They have all the features that waves have. Some seismic waves also travel at an interface. Which ones? Okay, so we're going to talk about that. Check on what your prior knowledge is. So if I have a wave, I think we need more light. Kind of dim. Good to go. Ah. Oh no! It's really not a great even wave there, but if we're talking from here to here, what is that known as?
Wavelength.
A wavelength. Now, usually in a definition for wavelength, they'll say from crest to crest or trough to trough. But as long as you're picking the same point from one wave to the next, you're okay. You can measure it that way. Yes, wavelength. Question.
Yeah, like some earthquakes.
Yes, if they displace water, or if there's a landslide and it displaces water, yes. Absolutely, earthquakes can cause tsunami. All right, so we've got wavelength. How about from the highest? What would we call this? Crest to the trough. What's the distance from the crest to the trough? Not frequency. Amplitude. How many of y'all say amplitude? From the crest to the trough, it's twice amplitude because there's a center line. There's a center line. Amplitude is from that center line up to the crest, or from the center line down to the trough. Does that make sense? So if you're actually measuring from all the way at the top to all the way at the bottom, that'd be amplitude times 2, right? And then somebody said frequency. If I was picking a point along the waves and the waves are coming this way, I could like start a stopwatch and count how many wave crests or troughs come by within a certain amount of time, and that's the frequency, how often they come. Does that make sense? Yes, if they're closer together, relative to the speed versus longer apart, it would have a higher frequency. So, yeah, usually it's like waves per minute, per second. If you're talking about like electricity, then you're talking about hertz, which is per second. No, not nanosecond, per second. All right. Seismic waves. Guys, the name of this lesson is seismic waves. Keep that in your forehead. They're energy released from the earthquakes. So the energy is released from what? What term? What causes the earthquake? A break, right? What do we call the spot where the break occurs? The focus. So the seismic waves emanate, they go out from the focus. Good. All right. Seismic waves can be broken down into two types. Body wave. You might want to put this in your notes if it's not in your forehead already, all right? You have body waves and you have surface waves. Body waves go through the what of the planet? The interior. The body. They go through the body. They go through the crust. They go through the mantle. Some of them can go through the core, yes, depending on the type. What is funny? What? What? Yeah. Okay. Getting old. Surface waves, on the other hand, travel up at the surface. All right, then we can break those categories down into two each again. For those of you that are taking notes, that's great. Primary waves and secondary waves are the two categories of body waves. So those are the ones that actually go through the earth. Does that make sense? Okay. Primary waves are faster. Has anybody ever played with a slinky? Yeah. Let me switch the question. Who's not ever played with a slinky? Okay, good. So imagine I have a tabletop right here, and I'm holding a slinky on either end, okay? I've got it kind of stretched out, not too far. And I go like this on one end. What is that going to do? It's going to go down and back, right? And the wave is at a right angle to the direction of travel of the energy. Does that make sense? Okay. That's called a transverse wave or a secondary wave, or you could use the term shear wave. All right. A compression wave, P wave, is if I took that spring and I went like this, like compressed it in line with it. Does that make sense? It's also known as a longitudinal wave. So I'm compressing a section of those springs, and that compressed section is going to travel down, bounce off, and then bounce back or reflect. The compression waves are faster. They can also travel through solids, liquids, or gases. You hearing the sound of my voice right now is because of compression waves going through the air. Does that make sense? Transverse waves don't work that way. They have to go through solids. Okay? Here we have a hammer striking the bottom of a column of whatever material this is, and it's showing that compressed section traveling up through that column. Here we have a hammer striking sideways, producing a transverse wave, and you can see that like that bulge wave traveling up the column. So those are your body waves. Surface waves, we've got love waves, which go side to side. I think the reading says something about like a snake moves. And then Rayleigh waves, undulate. They go up and down. Okay. And they have specifics on about how fast they are. Summary, we're already there. Body waves travel through the body of a planet. S waves travel along the surface. There are two types of body waves. P waves travel fastest, and they can go through solids, liquids, or gases. S waves only travel through solids. Surface waves are the slowest, but they do the most damage because they're near the surface where our structures are. Any questions on any of it? Okay. I think I already signed it, didn't I? Yeah. So you guys are released to go ahead and work on it. And keep in mind, plate tectonics test late next week.